Legendre polynomials are one of those mathematical ideas that sound intimidating when you first hear the name. But underneath that formal title lies a very practical and beautifully structured tool used every day in physics, computer graphics, engineering, and even planetary science. You can think of them as a special set of shapes, curves, or patterns that help us describe complicated things in a simple, organized way. To understand Legendre polynomials, it helps to start with a bigger idea. In math and science, we often want to describe how something changes. This could be how gravity varies around a planet, how light scatters when it hits a surface, how a field of temperature behaves over an object, or how a wave wiggles in space. Real-world behaviors are rarely perfect straight lines. They bend, twist, and curve in complex ways. Instead of understanding these behaviors all at once, we break them into fundamental building blocks, simple pieces that, when added together, reconstruct the full picture. Legendre polynomials are exactly that, simple, well-behaved building blocks for describing functions and patterns that change smoothly in one dimension. Think of them as a set of standard curved templates, each with its own personality. The first one looks very flat and boring. The next bends gently. The next wiggles a little more. As you go to higher and higher ones, the curves get more complex, with more bends and twists. But every one of them fits inside the same interval and obeys the same set of rules. The key feature that makes these curves useful is that they are independent. In simple terms, none of them can be made by combining the others. Each one contains a unique shape that cannot be replicated by rearranging or scaling the earlier ones. This is incredibly helpful because if you want to describe a complicated curve, you can mix these independent shapes together like ingredients in a recipe. You might take a little bit of the first one, some amount of the second, and a smaller amount of the third, and so on. By adjusting the weights, you can approximate almost any smooth curve you want. Another important feature is that Legendre polynomials are balanced. Imagine you drew one of them on a piece of paper and folded the paper in half. Many of them have symmetrical behaviors. Some mirror perfectly, while others flip their sign. This symmetry keeps calculations stable, removes unnecessary distortions, and makes them ideal for solving physical problems where balance and fairness matter, like gravitational fields or electric potentials. One of the biggest areas where Legendre polynomials appear is in solving what are called boundary problems in physics. For example, if you take a planet, the gravitational potential around it is often not perfectly smooth or uniform. To study it, scientists expand the gravitational field into Legendre polynomials. Each polynomial describes a particular pattern of distortion. Maybe the planet bulges slightly at the equator, maybe it has some uneven mass inside, maybe it's spinning. Instead of wrestling with the entire field at once, we break it into neat, manageable pieces. The first polynomial represents the simplest part of gravity. The next represents a slightly more complex distortion. Higher ones capture finer details. Add them all together, and you recreate the planet's full gravitational personality. They also appear in computer graphics. When rendering light on 3D surfaces, especially for realistic shading, Legendre polynomials help approximate how light bounces. Light hitting a surface does not simply bounce off like a mirror. It scatters in many directions. These patterns of scattering can be represented using the same kind of building block, idea, and Legendre polynomials give a compact and efficient way to estimate how the illumination behaves. In engineering, they help solve problems involving vibrations. A vibrating string, beam, or bridge can move in many complicated ways, but once again, those motions can be broken into simpler patterns. Legendre polynomials provide a framework to describe the possible shapes of vibration cleanly and predictably. Another intuitive way to think of them is as neutral curves. Many polynomial shapes tend to shoot upward or downward wildly when you stretch them across an interval. Legendre polynomials, however, behave very gracefully. They don't explode unpredictably. Their peaks and troughs occur in orderly places. Their oscillations are smooth and evenly spaced. This makes them extremely stable in calculations. When scientists and engineers design algorithms, they love tools that behave predictably, tools that don't swing out of control or blow up under small changes. Legendre polynomials provide exactly that stability. even though they were discovered in the early 1800s by the French mathematician Adrien-Marie Legendre. Their usefulness has grown dramatically with modern computing. Many numerical methods today rely on them. When computers approximate curves, estimate solutions to difficult equations, or simulate physical systems, they often rely on grids or nodes. Legendre polynomials naturally produce ideal sets of nodes, points that are distributed in a way that minimizes error and improves performance. This has led to highly accurate methods used in weather prediction, fluid simulation, aerospace engineering, and climate modeling. Perhaps the most impressive thing is that Legendre polynomials form a complete system. This means you don't need any other types of curves to approximate a nice, smooth function. Just these alone are enough. It's like having a perfectly curated toolbox. Each tool has its purpose, each works harmoniously with the others, and together they can build almost anything. In summary, Legendre polynomials are a family of beautifully organized curved shapes that help us describe complex behaviors in a simple, structured way. They are stable, balanced, independent, and powerful. They let us break difficult physical or mathematical problems into smaller, simpler components that can be analyzed, computed, or simulated with clarity and precision. Although their name may sound abstract, their impact reaches deep into physics, engineering, graphics, and many modern technologies. They remind us that even the most complicated patterns in nature can be understood when we choose the right building blocks.